Now we have to solve these two ordinary differential equations. I will start with the first one here. This is just a first order ordinary differential equation, and it can be solved by separating the variables here, time and the function u1, because we have I h bar du1 over dt equal to e times u1, which we can rewrite as I h bar du1 over u1 equal to e times dt. Okay, so we have separated the variables u1 and time. On the right we have time, on the left we have u1. And of course we can integrate both sides of the equation. I h bar logarithm of u1 equal to e times time plus some constant, okay, plus some constant here. And of course if you divide by I h bar and you relabel the constant in a different manner, you can find that u1 can be written like this. We have some constant that I can call a times the exponential e raised to the power et divided by h bar. We also have a factor of I here, which appears in the denominator, or if you want you can put minus I like this, because 1 over I is just equal to minus I, because I squared is equal to minus 1, of course. Okay, so this is the solution for the equation that depends on time. And we will see that this solution will be the same in every zone. Okay, this is the time-dependent part of the Schrödinger equation. But what's really important is the time-independent part, which is this quantity, this equation here. This equation is also called the time-independent Schrödinger equation. And we have to solve that equation now. So, in particular, for a second-order differential equation like that, we can solve it like this. So, when you have a second-order differential equation which is linear and the coefficients are constant, you associate with the second derivative there a scalar, which is just, we can call s, and we will raise it to the second power to replace the second derivative. Whereas we will have to replace w1, if you want you can think of it as the zero order derivative, by s to the power 0. So this power here, 0 here, is just the power of the derivative there. And of course the function itself is the zero order derivative. So we have s to the power 0, which is just equal to 1. So here you multiply by 1. And here this power of 2 represents the second order derivative there. Okay, so what you have to do is you have to solve for s, and in this case s is just equal to plus or minus I square root of 2me divided by h bar squared. Okay, and now that you have this solution, so you have the algebraic solution, and now that you have the algebraic solution, you can write the solution for w1 of x, because this s here is just the solution to, so if you replace, for example, if you substitute e to the plus or minus s times x, you will see that if s is defined like this, then this is a solution to the time-independent Schrödinger equation there. Okay, and since we have a plus or a minus, we can simply add the two solutions. So we have two solutions, e to the sx and e to the minus sx, and therefore we have something like this. So we have b, a constant b, times e to the sx, which is I square root of 2me over h bar squared times x, plus some constant c times e to the minus I square root of 2me over h bar squared times x. And this is of course true if the energy is greater than 0, right? Because if the energy were less than 0, then we should have defined S in a different manner, because in that case, if the energy is negative here, you will get another imaginary unit that multiplied by this imaginary unit will give us a real solution in that case. So if the energy, for example, were negative, now this is a very general solution, we are considering negative energies here, but we will be interested in this part E greater than 0. Okay, so I'm going to write down the solution also for E less than 0, but we will not use that. So we have B prime, some constant that I will call B prime, times E to the square root of minus 2me divided by h squared times x plus C prime E to the minus square root of minus 2me over h bar squared times x. And if you want, you can also consider the energy equal to 0. So when you have the energy equal to 0, the solution to the differential equation there will simply become double prime equal to 0. So the solution will be something like this: B double prime times x plus C double prime. Okay, but let me repeat to you that what we will consider is the energy greater than 0 here. So this is what we'll be interested in. In particular, these terms, this one here and this one, represents some waves, okay? And these waves are the propagation of the particle. When we consider the motion of the particle, for example, we will consider a particle that from the left is approaching the barrier. And in particular, the incident wave is this one here. This is the incident wave. Why is it the incident wave? Well, because we have e to the I square root of 2me over h bar squared times x. And also remember that when we want to consider the function psi1, we have to multiply w1 times u1. And u1 is some constant that multiplies e to the minus I e over h bar t. Okay, so if you put them together, you have e to the I square root of 2me over h bar squared times x minus e over h bar t here. So you can see that the wave here is propagating from the left to the right, because if you increase the variable time here, in order for this quantity here to be a constant, the wave is moving like this, because when the variable time increases, in order for this quantity here to remain constant, we will have to increase x as well. So this is one way to see that, because we have to set that equal to a constant, because that's, let's say, a point of the wave. Okay, so it represents the wave itself. So the particle, the wave is moving in space, and it is moving also in time. Okay, so when we consider the wave, we have to set that equal to a constant. Okay, you can think of that as the surface of the wave, for example. Okay, and if we put a minus sign here and minus sign here, which is this other solution, then it means that the wave is propagating from the right to the left. So this is also called the reflected wave. This is important. And what is it reflected by? Well, it is reflected by the barrier. Okay, because when the wave is incident upon the barrier, then the barrier is going to reflect the wave, and some part of the wave is going to penetrate the barrier. Okay, so this is what we will see also in the solution for the second zone. Remember that we also have to solve the Schrödinger equation in the second zone, where x is between 0 and L, and we will do it next time.